Okay. So far we learned the convolutional neural network before the class. Before this lecture, we learned about the deep learning and also CNN architecture. And today we will learn about how to implement such deep learning easily using Python language. And especially we will use this PyTorch library. This is the library that help you to implement deep learning algorithms. Okay. So there are some other libraries, but in this lecture, we will use this PyTorch. This is developed by Meta. And there's another famous library whose name is TensorFlow. This is developed by Google. But I mean, this PyTorch provides more flexible feature. So we will learn this during this course. And also, if you write some code for the assignment, you have to write all the code in this lecture using the PyTorch because we learned this. Okay, don't use TensorFlow. Okay? And this is the thing we learned so far. So given this is denoting some deep learning architecture. This is denoting some deep learning architecture, and this is the function that can calculate the loss, okay, from the final prediction y. We represent this as the layer because this is also the differentiable operation. So somehow we calculate the distance between final predictions of the deep learning architecture with the ground truth by subtracting them and applying this kind of Euclidean distance, maybe. And some other loss functions are ready. But these kind of operations are differentiable. Their output is differentiable to, if this layer is formulated like this, then this layer is differentiable in that their final output is differentiable with respect to their input, and there's no parameter. But anyways, I mean, this parameter update rule have to be calculated, but this loss layer don't have any parameters, so we don't have to calculate this. And this, the differentiation of output respect to their input, we can calculate that, okay? So in that sense, we can also interpret this loss calculation as the layer. Anyways, when we can calculate these two gradient values, then we can eventually calculate this differentiation of the final loss respect to all the parameter sector inside the deep architectures. So this sector is denoting the parameters of the deep architectures, and this is denoting the loss. And this direction, DLD sector, is denoting where to update parameter sector to minimize this loss L, okay? So, and this formula is meaning we update previous parameters to that direction by multiplying some small epsilon value, okay? Epsilon values are, for example, initialized to this small scalar value, and we calculate the new parameters. So that's this gradient descent formula, okay? So everyone following this, okay? So we are uploading all the lectures in the YouTube. In the Blackboard, you can, easily search for the link to the YouTube. So if you think something is missing, then please watch that again, okay? So this is something we learned so far. And we will now learn about this PyTorch. And when you try to implement this forward rule and backward rule and parameter update rule you may feel implementing the forward rule is rather easy, okay, but implementing this backward part, calculating the gradient, is not that simple in the, I mean, it is not that trivial to implement this in the code level, okay? So for example, let's say your forward rule looks like this. So let's say this is example. So your input is X, okay? And your output is Y. And this is some parameters for that layer. Then you have to calculate this to gradient. I mean, you have to write down some formula for calculating this gradient. So for example, dy dx is this. Okay, you may manually calculate this like this, right? And also dy dz, you can calculate that as x squared. Okay, is that true? So you have to calculate this by yourself, given one forward rule, and you have to write code for backward, forward, and parameter update rule by yourself. So in the code level for each layer F, you have to make some code method like this. So X and return. So you may have to write the code for this forward rule, right? And also you may have to write the backward rule. Which one is backward? This one is backward. So sector multiplied by 2 multiplied by x. You have to write down this kind of code, okay? And for parameter update rule, you have to write down this kind of code by yourself, okay? When implementing forward rule, backward rule, and parameter update rule for that specific layer, okay? But sometimes, I mean, you cannot easily, trivially calculate this gradient. And also the important thing is, if the forward rule changes, you have to recalculate backward rule and parameter update rule, okay? Is that true? If forward rule changes, their gradient also changes, okay? And you have to implement this method again by yourself, okay? But this is not easy because deep layers have many layers, and I mean, we cannot easily calculate and also easily implement all the method by ourselves because there are too many layers, okay? So PyTorch is actually helping us to implement these huge deep networks, okay? So what they are doing is they somehow provide some, how to say, automatic gradient calculation function. So rather than calculating this gradient manually and implement that in your method by yourself, there are another way to calculate this kind of gradient in the, using some iterative algorithms. Maybe I think you already learned about this kind of iterative algorithm, like the Newton algorithm. in the calculus course. If you do not learn about that, don't worry. Anyways, I'm certain that but there you can say that there's some iterative algorithm to calculate the gradient values given the forward function. So this iterative algorithm is not actually approximating the gradient values given the forward rule. And that is some algorithm to calculate the gradient given any forward rule. So the important thing to note is this algorithm does not changes depending on the forward rule. Are you following this? So if you calculate your gradient by your hand and implement that by the manual effort, then this parameter update rule and the backward rule always changes. Okay, but if you use this kind of iterative algorithm to calculate the gradient, then this algorithm doesn't change. So it makes your parameter update function and also the backward function does not change depending on the forward rule. Okay, you will apply the same algorithm that can calculate the gradient, okay, regardless of the forward rule. Okay, so in the PyTorch, this kind of automatic gradient calculation algorithm is already implemented for parameter update rule and also the backward rule. Okay, are you guys following this? So maybe I will show you the code actually implementing each layer in PyTorch later. But you can see that there's only the implementation for the forward rule, and there is no implementation for the backward. Because that part, the PyTorch can automatically calculate it using this kind of approximation algorithm and also the backpropagation algorithm you saw last class. So for each layer, this backward rule and parameter update rule are calculated by this iterative algorithm. And also by merging these layers, you have to calculate eventually the differentiation of loss respect to each layer parameters. That part you will have to using some backpropagation algorithm based on the chain rule. Okay, so we actually learned about that last class. So you don't have to implement this parameter update rule and also the backward rule in your layers when implementing the deep learning algorithms, deep architectures using the PyTorch. And the thing you have to do is very simple. The only thing you have to do is, calling these two functions. If you call loss.backward, it calculates DLD sector for every parameters. Okay, so these values are calculated for all the parameters if you call this loss.backward function. I will re-explain this in the context of the whole code later slide. But anyways, if you call this function one line of code, DL dissector, which is this, is calculated. And also, if you call this one line of code, optimizer.step, then this is calculated once. So the parameters are updated once if you call this function. Okay, are you guys following this? Okay, so by these two lines of code, this is calculated for the entire deep architecture, and this is actually meaning training the network. Okay, are you guys following this? This is very important, actually. So if you don't understand this, please raise your hand. Okay. So this is important two lines of code in PyTorch. And I will explain this in the context of the very simple machine learning algorithm whose name is linear regression. Linear regression. So I already told you that this linear is meaning that this kind of function. Okay, I believe all of you are familiar with this kind of linear equation. In Korea, it's 1차 함수, maybe. Okay. So this, when you draw the curve of this equation, that it would be the straight line. Okay. So we call that as the linear equation. And regression, that is one branch of the machine learning algorithm. So there are actually classification, regression. Actually, machine learning algorithms are classified mostly into these two classes. Okay. So the classification, they actually output the function f. If we input some input x to this function f, then this y would be outputted, and this y is meaning some category, some discrete category. Okay, so for example, in image classification, each output y is denoting the image category, dog, cat, or other animals, or other, anyways, semantic category. Okay, so this y is meaning some index for that semantic category. So in classification, their output has, output itself has some integer number, have no meaning by itself, but it is directing some semantic class. Okay, are you guys understanding this? But in regression, we are, if we input x to the function f, then it will output something, and that output is having some continuous value. For example, let's say the x is some weight of a person, and we can train some function f that can map weight to the height. Okay, so in this situation, the output itself has some semantic meaning by itself. So the output is not integer, pointing out some semantic classes, but the physical values in this regression task. So the output itself has some continuous value, and it has some meaning by itself. In that problem, we are saying this as the regression task. Okay, so we will first deal with linear regression task. We will call this as the linear regression because the output should be correlated with the input x via this linear relationship. And also the output is some continuous value. So we will call that as the regression task. So we call this as the linear regression algorithm. And this is most simple machine learning algorithm for the regression task. Okay. So for example, this is the y value, which is the output. And this is the input. Okay. You may think this is some weight of a person, and the output could be some height of a person. And weight and height, they are having some correlation between them, right? So if a person is their height is, height is having the high value, then it is their weight also be high. Okay, there's some correlation between height and weight of a person. Okay, so when the weight of a person is given, we somehow can estimate their height value. Okay, so and this regression task, we will use the straight line. These blue points are actually the data given to us. This is the data given to us. This is denoting some weight and height of a person. And this is also denoting some other person's weight and height. And this is same, okay? And our mission is to find the straight line. Finding the straight line is same as equivalent to finding this parameter A and B, okay? And we can say parameters also, always in terms of parameter sector, and we can say it like this. So we have to find the parameter sector, which is actually the A and B for this linear equation, okay? If we can find this A and B, then we can find this straight line that correlate this input and output. Okay. So that is actually the linear regression task. Okay. So are you guys understanding linear regression here? Okay. And there's several ways to find this formula. There are some various ways, multiple ways. As far as I know, there are more than five ways, but we will find that A and B, the parameters for this straight line, using the gradient descent algorithm, the one we learned. Okay, we will use this to get this A and B, which are the parameters for the linear equation. Okay. Actually, in this code, we denote this A as Wx plus B. Okay. We usually use W for this A and B for this constant term. Okay. So this is actually the code for finding this W and B, which are the parameters for the straight line given data. Okay, I will explain that. Sorry. So this part, we will generate data first. And this part, we will find our sector, which is W and B. Okay. Here, I will, I will explain this first. This W true and B true are some true W and true B value. So, in this case, This is not constant. This is some vector in our case. So this is actually looks like this. Sorry, transpose is here. So are you guys understanding this matrix multiplication? Okay. So our output Y is, having multiplied with this W matrix. This is our actually input having 3 dimensions, and they are multiplied with 3-dimensional vector, and this constant B, the scalar value is added to get this Y output value. So our aim is finding this W matrix and also the B constant given many Y and X pairs. Okay, so we will call this pair as the data. So we have to secure many of this pair, and we will call this as our data. Okay, and here we will define some true W and B. This is some W true, and this is the B true. Okay, and using this W true and B true, we will make the data by these 2 lines of code. This is actually making the data. So X values is randomly sampled. So 100 samples for this 3-dimensional X1, X2, X3. This 3-dimensional X vector is 100 times randomly sampled. And for that randomly sampled input X, we will multiply W true and will add B true to get some Y value for that random X. So this is actually code for making 100 random data. Okay, are you guys following this? And also, so these 2 lines of code, these 2 lines of code define the W true and B true, and these 2 lines of code is randomly sample input value 100 times first, and for that random input, we will generate some output, ground truth output for that. And these WB are the initial sector. Okay, sector is actually W and B in our case. And these W and B are randomly initialized at the first stage. So we randomly initialize it. Okay, so starting from here, we will apply the gradient descent algorithm to update this based on this DLD sector. And we are expecting actually this goes close to the W true and B true values eventually. Okay, are you guys following this? Okay, and this gamma is the small value epsilon. Okay, and this is the matrix. We will store our loss function at each epoch in this empty variable. Okay, and this part is the code for iterating for this gradient descent algorithm. So this part is for calculating this gradient descent. So for each variable inside the PyTorch, we actually have 2 values. So for this W variable, we actually have 2 instance variable. If you call this w.data, it actually have the value. So it actually have value. And if you call this w.grad, then it stores some gradient value. So actually the gradient means this one, dw. Actually you will have this dl dw. This value have dl dw. Okay. So, but at the initial stage, you have to initialize each gradient. Okay, w.grad and b.grad. It have to be, initialized by known value. If it has some initial value, then if you call this low start backward, actually this is calculating DLD sector for every sector inside the deep architecture. And after that, actually it is added to the initial value. Okay, so if you do not initialize them with the known value, actually they are added with the new gradient value. So the entire value is not correct. So you have to first make it known and then call this low stop backward to secure this correct gradient could be added to the zero value. Okay. So you have to first make it initialized. And the thing you have to do is you have to calculate one forward path. Okay. So given data X, you will calculate one forward path, which is this Y is WX plus B. This is the forward rule for the linear regressor. Okay, this is the input. For the input, you will multiply W matrix and will add some constant B to output Y. And this is the forward rule. So this is actually denoting that. So your prediction Y will be calculated like this. And this is the loss calculation. Your ground truth Y is compared with the predicted Y. And this is meaning the power of 2. So it is actually calculating this kind of Euclidean distance, okay, between these two values. And actually that's the loss function. So this is actually calculating one forward path the loss function. Okay. Are you guys following this? And after that, we call this function loss start backward. Okay. And as I told you in previous slide, if you call this loss start backward, these values are calculated for every layer's parameters. So actually, this is calculated for every parameter, which is the W, and now the W, now the sector is W and B for whole the deep architecture. So DLDW and DLDB are assigned to W.grad and also B.grad. Okay. So when you call this, all the gradients for every parameters are calculated automatically. And after that, you can update each parameter W and B using this kind of formula, gradient descent rule. So this is the previous parameter value, and you will multiply small learning rate on that for the, the gradient value, okay? And then this W and B are updated once. And we will store our current loss, which was calculated here, okay? And this is iterative through the 100 iterations, okay? Are you guys following this? So this part, we make some 100 X and Y pairs. And here, we initialized the W and B randomly first. And through these 100 iterations, we are expecting that by applying this kind of gradient update 100 times, this randomly initialized W and B are becoming similar to the W true and B true values. Okay. So this is actually printing out the W and B, which are applied 100 times with the gradient descent update. Then its values are like this. And this is the true W and true B values. This is true B and true W value. And actually you can compare that are same, okay? And this is denoting the losses. We stored the losses. Initially, it was the blank array. And here we append current each iteration's loss values in this variable, losses. And if we visualize it, it could be look like this. The x-axis is denoting the iteration number. And this is the loss value. You can find that losses are quite high, which means the distance between ground truth and our prediction, okay? That's very high at the initial step because our parameter, which are W and B, are randomly initialized at the first stage. But as W and B becomes smarter, then loss, which is the distance between ground truth and our prediction, reduces gradually. And actually, it goes close to zero. So you can see our W and B are actually becoming close to the ground truth, W and B. Okay? Are you guys understanding this? 혹시 이해 안 되면 이거 이해하고 넘어가기 바랍니다. Okay. And one thing you have to remember here is inside the PyTorch, as I mentioned to you, each variable B, X, and W we defined in the middle of the code are having two values, data and gradient. Data, it has some value, and gradient, grad, instance variable, it has the gradient value. And if you want to access the gradient value itself, you have to also access this data instance variable again for this grad instance variable. Anyways, inside the PyTorch, these variables are first defined. B, W, X, they are first defined. And inside the PyTorch, they somehow connect these variables using the operations. When we do this, when we define this forward rule, this kind of graph structure is constructed inside the PyTorch. X and W are connected with this multiplication, and this intermediate output is connected with the constant B with the plus operation, okay? And this is the output Y, okay? So, I mean, given this code line inside the PyTorch, they somehow construct this kind of graph, okay? And using this kind of graph, you can apply backpropagation we learned. So I showed you using this kind of graph, graph, we can step by step calculate the gradient value for each node, okay? And this kind of graphs are constructed until the final loss is defined. Are you guys understanding this? So this is the initial variable, and actually we define our forward rule here, and we also define how losses are defined using this output, okay? And the rightmost node would be the loss L, okay? And given this loss L, we can always calculate this DL dissector by backpropagating this graph, okay? So in that way, we can calculate all of these gradients, okay? And also for individual gradient, we can apply some automatic gradient calculation algorithm, okay? Which is same for all the forward function. So, I mean, this kind of gradient calculations that happen when we call loss dot backward function, okay? I mean, if we define forward rule, this kind of graph structures are defined until we get the loss function L, okay? After that, we can, we already know the connected variables. So we can calculate the gradient values for all the variables. So using that knowledge, we can calculate this DL dissector by calling this loss dot backward, okay? And then using that, we can update it once. And later I will show you, this part is also simplified to optimizer that step, okay? So I mean, deep architectures have many parameters because they have many layers. So W and B specifying these individual parameters are, tedious because there are too many parameters. If this linear regression have just one layer, having just this formula to get output from the input X. So this is very simple to implement. But if you have like 152 layers, then there are many parameters you have to specify. So when specifying that, you may need 200 lines of code. Okay, it's too many to specify individual parameters. So the PyTorch also have some list for individual parameters inside. Okay, and rather than specifying this gradient update rule for individual variables, it provides one function that can do applying the same rule on the different variables when calling this one line of code. Okay. So I will re-explain that afterwards. So from now on, I will show you the PyTorch style code. Okay. As I told you, this is the code for implementing very simple linear regression algorithm. Okay. It has only two parameters, W and B. But in the modern deep learning architecture, it has very much parameters inside. So defining that variables may cost more than 1,000 lines of code, maybe. Okay, it's very tedious. So in PyTorch, it provides the interface for defining this kind of architecture. So, I mean, we can define some architecture as the variable, and we can define it like this. So, because we are now having just one layer, that operations like Wx plus b, this kind of operation is called as the linear operation in PyTorch because they are linear equations. The PyTorch define it like the linear operation. And we can specify the input feature dimension and output feature dimension and whether we will use bias or not. If this variable is false, then the final variable, the equation looks like this. But normally we use this kind of linear equation which have a bias. This is called as bias. And as I told you, this has the three-dimensional vector. This is the three-dimensional vector. So input features, their dimension is 3. And the output feature, that dimension is 1. So we can, by specifying this input dimension and output dimension, and whether we will use bias or not, this linear operation could be defined in the PyTorch. Okay. And that layer, that architecture is named as net. Okay. So this is more desirable coding styles in the PyTorch. Okay. By defining this one line of code, I mean, you don't have to specify each individual parameters. And also, this kind of forward rule, previously we defined it by ourselves, but this is already defined when this layer is made. Linear operation is looking like this. So, and we don't need to anymore specify their detailed operation. Rather than that, we can just specify the architecture's name and also the input value. And this is the output value. Okay. So this is a more simplified Python grammar. This works, and this is also works in PyTorch, but this is more desirable semantic, more semantical code style in PyTorch. And also, this is the gradient descent update part in previous code. Okay, we have to specify each individual parameters and assign known for each individual parameter, and have to update this with the manual effort. But rather than that, this is more desirable. We explicitly define some optimizer. These kind of things are called as the optimization algorithm. Gradient descent is called as the optimization algorithm. So we will explicitly make some optimizer that can lead this optimization step. And this algorithm is called as the gradient descent algorithm. So this SGD is the abbreviation for stochastic gradient descent. I will let you know what's the difference between SGD and GD later. But anyways, we will use this SGD function which implement this gradient descent. Okay. So this optimizer will lead us for this gradient update. Okay. And it has to know two parameters. Net dot parameters, it is meaning the sector, the parameters of our defined network. Okay. This net dot parameters, by calling this the learnable parameters their lists are returned. So the optimizer have to have the list of the parameters which will be updated. So this is the first argument. Okay, are you guys understanding this? And the second argument is the learning rate, which is the small epsilon value. So this have to be also specified for optimizer. So optimizer will proceed this gradient descent, and it have to have the list of the parameter sector. That's the first argument. And the second argument, it have to know the second epsilon value. Okay. Then next, the thing you have to know is this, right? So this part we will calculate by calling low start backward. Okay, and we already know this by the second argument. We already know this sector because we specify the sector list here. So after calculating this low start backward, the next thing is calculating this. Okay, so when specifying optimizer will do this optimizer.step by calling optimizer.step. I mentioned that this formula is calculated, right? So we already calculate this DLD sector by calling low start backward. So we now all know each term of necessary values. So we have to calculate this once, and that part could be achieved by calling this one line of code, the optimizer.step. Okay. And we have to, reduce this code, not making the users not calling individual parameters separately. This one line of code manages all the parameters we have to update, okay? And when this is calculated, then manage to update this for all the parameters by calling this one line of code, okay? And also for the loss function, this is the loss function, calculate the distance between prediction and ground truth using the Euclidean distance formula. But that is already defined in the PyTorch as the MSE loss. This MSE mean square error. Okay. Mean square error is actually same for the Euclidean distance. So this loss function is already defined, or you can change this to other loss by replacing this function to others. Anyways, you have to define loss, and rather than specifying rather than specifying the detailed operation for calculating the loss, you can just specify mean square error loss because it's very popular already. So the thing you have to do is just calling this loss using two parameters. This is the predicted value, and this is the ground truth. This is the prediction, and this is ground truth. You will input these two as the argument for this loss function now. Okay, this is more desirable feature for the PyTorch. Okay, so you can now see that this iterative step becomes very simple. I might miss this part maybe. So previously, this known value is assigned individually for individual parameters, but by calling this optimizer.0_grad, you can do this automatically for every parameters. I mean, if the parameter numbers are becoming larger, calling this function also requires multiple, very large number of lines of code. So rather than that, by specifying it using the optimizer, you can simplify the code. Okay. So the resultant code becomes like this. So first, you have to initialize. So in this gradient update rule, you have to make this 0 first by calling this one line of code. And you have to call the forward function once and calculate the predicted value and compare it to the ground truth value and calculate the loss. Okay. And by calling loss.backward, this is updated to some real gradient value. Okay. By calling this. Okay. So you calculate this, and this epsilon is already defined here. Okay. We already know this. And this is already known here. After calculating this, the only thing remained is applying these ones, and that is here. Okay. So this will calculate this formula once, and losses, the current losses stored in the variable. And this is iterated for 100 iterations. Okay. So, and these are for visualization. Okay. So this gradient update rule, when implementing this gradient update rule using the PyTorch, this becomes very simple. And actually, even though your networks are changed, or if you use another optimizer or use another loss function, the thing you have to do is changing this part only, and this updating code does not change. Okay, maybe you will feel this when seeing the real code when doing some assignments maybe. So this actual gradient descent update code is not changed much, even though your architectures are changed or your data are changed, or optimizer you will use is changed, or the loss function is changed. Okay, these 5 lines of code does not change much. Okay. Okay. So this is the introduction for PyTorch. Okay. So I strongly recommend you to be familiar with these 5 lines of code implementing the gradient descent. And now I will show you one another machine learning algorithm called as the multi-layer perceptron. Okay, so its name is multi-layered perceptron because it is composed of multiple layers. Okay, linear regressor we just saw have only one layer whose operation looks like this. Okay, multi-layer perceptron, whose abbreviation is MLP, it has multiple linear operation inside. So this is input and this is output. For getting output from input, you will apply multiple linear operation. Okay, so it has multi-layers. Okay, so it is inspired by the human brain. So each linear operation looks like the neuron inside the human brain, and we combine that to represent the final output. So anyways, these MLP layers are inspired by the human brains. And in the middle of the MLP, we always have to have some activation layer, as I mentioned to you previously. Without that activation layers, which is the nonlinear component, the entire multi-layer perceptron becomes another huge linear operator. So to prevent, this is not desirable characteristic. So to prevent this, we apply some nonlinear operation in the middle of these MLP layers. Okay. So, and this nonlinear layer, we will use ReLU and some sigmoid or tangent hyperbolic we saw in last class. Okay. And this is actually the MLP we can define in the PyTorch. This torch.nn.sequential means we will stack multiple layers sequentially. This is meaning we will stack multiple differentiable layers defined in the PyTorch one by one. So we will stack firstly one linear and ReLU, one linear, ReLU, one linear, ReLU, and apply final linear. So it is implementing this kind of linear, nonlinear, linear, nonlinear, linear, nonlinear operation. Okay. So when you implement it in the PyTorch, it looks like this: linear, nonlinear, linear, nonlinear, linear, nonlinear, linear. Okay. So our network is now obtained by stacking multiple differentiable layers whose order is like this. So this is actually meaning the MLP layers. And this is the data generation part. Similar to, today's linear regression example, we have to generate some data. And this is the loss function we will use. And this is the gradient descent optimizer. This is the same code for gradient descent, okay? So, using this, we can actually train MLPs. The thing you have to, fill here in this slide is that this code is same as before. So regardless of your networks are now MLP rather than the linear regressor, the updating code is not changed at all. And loss function and optimizer, they are also not changed. And only the part data generation is changed because we will use another data. Okay, and this network part is also changed, but seems very simple. Okay, so using this kind of code, you can train an NLP for this kind of dealing with this kind of data. Okay, so I will explain this in the Wednesday. Okay, so maybe this is for today's lecture. For the later part, we can learn this Wednesday. Okay, thank you. Let's finish here.